Okay, so welcome to sort of the first math lecture for Math 639. By the way, I don't always look like Bohemian, but I do now because we're officially, technically in the summertime. So this is a couple of weeks before the courses begin. This will be material for the first week of Math 639. So before watching this video, look through the material in sections 1.1 through 1.6 of the book. I'm going to basically assume that you know that material for this book. It's just basic linear algebra things. If you've had a basic linear algebra class, you've seen basically all of it. One thing that you might not have seen that will not be especially important for what we're doing today, and when it does become important, I'll mention it again, is going to be things on matrix norms. So probably you know what a vector norm is if you've read through those sections and if you've taken a linear algebra class, but you might not have seen a matrix norm. So look at that part at some point, but like I said, it's not going to be something that we'll talk about today. At least not in any serious detail. So the thing that I want to talk about today, or in this video, is I want to look at orthogonal vectors, projections, Gram-Schmidt process, this idea here. So to be able to understand this, you're going to have to understand what a linear combination is. You're going to have to understand basic matrix vector multiplication, matrix multiplication, which I'm actually going to go over that as well. You're going to have to understand what an inner product is, what it means for two things to be orthogonal, and that sort of thing. And so like I said, that's in those sections 1.1 through 1.6, or that would be covered in a standard linear algebra class. So please take some time to familiarize, or hopefully refamiliarize yourself with the items in those sections. So the first thing that I want to start talking about, which is very basic, is the idea of vectors. I'm going to proceed in the following order. I'm going to tell you what vectors are. I'm going to tell you what a linear combination of vectors is. I'm going to tell you what matrix vector multiplication is, and then I'm going to tell you what matrix multiplication is. And that'll be it for this video. And then in the next video, we'll look at some of those other ideas that I was talking about. So, what is a vector? Well, that is not a good marker. What is a vector? Okay, now the sort of smart aleck response is that a vector is an element of a vector space. Okay, so what is a vector space? Well, a vector space is a set of objects that has these algebraic properties you can do to them: add, subtract, there's a zero vector, and this sort of thing. And then these adding and subtracting, scalar multiplication satisfies certain properties. But for us, in practice for us, a vector in the n-dimensional complex space, which is denoted by Cn, so it's like Rn, but we are allowed to have complex entries, is basically just going to be a list of numbers. So we're going to have Z1 down to Zn. This is like a vector. Okay. Now, typically the letters that we use for the entries, I'm using Z there because that's a typical letter for a complex number. But let's say we call our vector V with an arrow over it, and then the components I'm going to call V1 through Vn. V1 through Vn, like this. Okay, so that's a vector, and all of these are complex numbers. And remember that real numbers are also complex numbers. So these could all be real numbers as well, and it would still be a vector in the n-dimensional complex space. Okay, so like I said, if you've taken a linear algebra class, you'll know that there's a more abstract definition of a vector and a vector space, and we'll get to some of that later. But for now, I just want to think about vectors in n-dimensional complex space as being a list of numbers like this. Now, we will see that there is some. This causes there are difficulties inherent in this, and we'll get to some of that in the next video. But for now, don't worry so much about that. Okay, so what is this is one vector. So if we have a vector space, we can add vectors together. And so for this definition right here, when we add two vectors together, we just add the components together. So for example, if I have a vector, let's say V, and its components are V1 through Vn, and I have a vector W, and its components are W1 through Wn, then their sum, V plus W, is just defined by doing the component-wise addition. So we're going to have V1 plus W1 all the way down to Vn plus Wn. And hopefully, if you're watching this video, you're like, yeah, dude, I know that's like the first thing that you learn in linear algebra. And that's exactly how I want you to be thinking right now. But I just want to make sure we're all on the same page. Now, this is a vector, and so we can add more vectors to this. And so when we do that, one other thing that we can do is we can multiply vectors by scalars. So over here, if this is a vector and lambda is a scalar, then what it means to multiply a vector by a scalar, we're just going to multiply all of the components by that scalar. So here lambda is a scalar, and again, when I say scalar, scalar just means a complex number, which could be a real number as well, since real numbers are complex numbers. Okay, so a linear combination of the vectors v1 through Vm is a sum of the form C1 times V1 plus ... plus Cm times Vm, where the C's are scalars. So C1, C2, all the way up through Cm are scalars. They're complex numbers. And if you haven't seen it, this little symbol that looks like a euro symbol, we're saying that these are in the set of complex numbers. Okay, and now for this definition to make sense, all of these vectors, v1 through vm, have to be in the same n-dimensional complex space. So it can't be the case that like v1 is a 3-dimensional vector and v2 is a 4-dimensional vector. They all have to have the same dimension. And this is called a linear combination. Okay, now linear combinations are extremely important in linear algebra. The vectors are kind of fundamental building blocks, and then we take linear combinations and get other vectors. So linear combinations are of fundamental importance in linear algebra, and we're going to see that in this class. Now, because they are so important, we have a special way where we can write a linear combination like this. And this is going to be through matrix vector multiplication. So a matrix, there's a couple of different ways to think about a matrix. We can just, basically we can just think about a matrix as being a rectangular array of numbers, and then we can provide some interpretation to that. So I'm going to think about, for right now, I'm going to think about a matrix in terms of its columns. So I'm going to make a matrix, I'm going to call it capital V, and I'm going to tell you what the columns of the matrix are. So the first column of the matrix is going to be a vector V1, the second column of the matrix is going to be a vector V2, all the way up to Vn. Okay, and again, you can think about them as being like these vectors over here, for example. Okay, so what are the dimensions of this vector, or of this matrix? Well, let's assume that all of these VKs are in n-dimensional complex space. So this is a column, it has n entries going down this way, this has n entries going down this way, this has n entries going down this way. So there are n rows, and there are m different column vectors, so there are m columns. So we're going to say that V is in the space C, and then now in the exponent, we're going to write n times m, meaning there are n rows and m columns. And now, if we have a vector V, actually I'm going to call it W. If a vector W is in m dimensional complex space, we can define the product of V and W in the following way. Let me actually specify what I want to call the entries of W. So we say that W is equal to W1 through Wm. This is in m dimensional complex space. So the m there and the m there, they're the same number. And then we define the product in the following way. V times W is going to be equal to little w1 times v1. So w1 times v1 plus little w2 times v2 plus dot 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 plus little wm times vm, like this. Okay, so v times w, we have this expression right here. Okay, so this is the standard matrix vector multiplication. Now you might be thinking, well, I haven't seen that before, because sometimes this aspect of matrix vector multiplication is not emphasized. Instead, you might be thinking like, well, I remember doing something like where I take this vector and kind of turn it sideways, and I multiply this vector by the top entries of the top row, and that's going to give me the top entry of this vector, and then I multiply it by the second row, that's going to be the second entry of this vector, and so on and so forth. Yes, those are identical ways of talking about, well, they are different ways of talking about the same product. So whichever way you do it, you're still going to get the same product. But this way right here emphasizes the linear combinations. And this is one of the things that matrix vector multiplication captures, is this idea of linear combinations. So this again is a linear combination. The only difference between this linear combination and the one over there is that over there I used C's and over here I used little w's. And just the reason is because V and W are typical letters for vectors, and so I just wanted it to be like that. Okay, so this definition of matrix vector multiplication can then be can then be sort of used to define matrix multiplication. Okay, so it can then be used to define matrix multiplication. But before I do that, I want to talk about a couple more things. So one thing that I should have mentioned before is that for this matrix vector multiplication to be defined, the number of columns in the matrix has to equal the number of entries in this vector here, because notice we're doing a linear combination. So if we had more little w's than vectors, we would not know, there would not be a way to choose which w's to use and which ones not to use, so that wouldn't be defined. And then if we had more vectors than w's, there would be some vectors without w's, and so it just would not be a well-defined thing. So at least under the normal definitions. So in order for this matrix vector multiplication to be defined, the dimension of the dimension of W has to match the number of columns of V. And notice what you get out, the type of thing you're going to get out are going to be the number, it's going to be a complex vector in the dimension space where the dimension is equal to the number of rows of V. So V1, V2, all the way through Vm are in Cn. So all of these vectors are in Cn, and so this linear combination here, that is the product of V and W, are going to be in Cn. Okay. Now we can think about matrix vector multiplication if V is a matrix it's an n by m matrix. It's an n by m matrix. This we might say induces a linear transformation from m dimensional space to n dimensional space. Then V induces a linear transformation from m dimensional complex space to n dimensional complex space. Okay, so what do I mean by that? So I have my matrix V. I'm going to multiply it by my vector W. Okay, remember that W, if I use these same letters over here, W is an m-dimensional vector, and this output, the product of V and W, this, as I discussed over there, is an n-dimensional vector. Okay, so W is an m-dimensional vector, and this is an n-dimensional vector. Okay, now if you are rusty on what it means for a function or a transformation to be linear, or what a linear transformation is, review that and convince yourself, or actually prove to yourself definitively, that this is a linear transformation that you put in. It was definitely a function. If we think about this as being the variable, okay, it's definitely going from m-dimensional space to n-dimensional space. Just show now that it satisfies the linearity properties. That if we have v times lambda 1 w1 plus lambda 2 w2, that this is equal to lambda 1 times v w1 plus lambda 2 times v w2. Let me make that a little more lowercase. v w2. That's what it means for the transformation to be linear. Okay, so this is important because it's going to tell us how we want to define matrix multiplication. Okay, so why is that? So let's say I have a matrix V. All of these VKs are in Cn. So if I do V times W, again I'm assuming that W is an m-dimensional vector, then I know that I'm going to get out an n-dimensional vector. But let's say the following. Let's say I have this vector here. This vector here is in Cn. Well, this is a vector in Cn, so I can now multiply this by a matrix over here. Okay, let's say I multiply this by a matrix that I'm going to call A. Now, this vector here, once you form the product, this vector has n entries, which means this vector, this matrix here, needs to have n columns. But it can be an L, there can be however many rows we want it to have in. If this is an n-dimensional vector for this matrix vector product to make sense, then A needs to be an L by n matrix. The n here is fixed, but L can be any integer that we want it to be. Okay, so now what we have here is W is in Cm, V sends it to a vector in Cn, and then A sends it to a vector in L. So overall we have a composition. This is a composition. And this composition, to sort of maybe not use sort of abuse notation here a little bit, this is a composition, and it goes from m-dimensional complex space through n-dimensional complex space, and finally we get out into L-dimensional complex space. Okay, now for things to kind of be the way that we want them to be, for products to be defined the way that we want them to be, we also really need this to be equal to AV times W. Like, we need these two things to be equal to each other. So whether we do the matrix A times a matrix V times W, or V times W and then multiply it by A, we need whatever matrix vector multiplication is going to define to be, it needs to satisfy this equality right here. Okay? If it doesn't satisfy this equality right here, then we've just chosen a bad definition for matrix multiplication. Okay, so how can we do that? Well, let's see what happens here when we do this matrix, when we do these compositions here. So let me fix notation here. So A, its columns are going to be A1 through AN. Okay, and let's come up over here. And I hate, well, that's probably a strong word. I do not like this whiteboard that I use. I would much rather have a chalkboard, but this is what they gave me. Okay, so if I do V times W, so let's sort of see what's happening here. If I do V times W, I'm going to have A, and it's going to be multiplied by V times W. Okay, so what am I going to get? Well, when we do this matrix vector multiplication, this is going to be W1 V1 plus dot 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 plus WM VM, like this. Okay, so this is a sum. So we're doing A times this sum. Okay, now notice what happens if I distribute the sum. We're going to get W1, or if I distribute the A across this sum, we're going to get W1 times A V1 plus dot 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 plus Wm times A Vn. Again, I'm implicitly using that this is a linear transformation, but this is just a product of matrix vector multiplication that it satisfies these sort of distributive properties that we expect multiplication and addition to satisfy. Okay, but now notice what we have here. Notice W is like the input vector, but now we have a linear combination of vectors. Okay, each one of these, A times V1, well, what is V1? V1 is a vector in Cn, and so A times V1 is going to be a vector in Cl. So this is a vector in Cl. All of these are vectors in Cl, and so this is a vector in Cl. And so we can simply write this in the following form. Okay, it's going to be a matrix. It's going to be a matrix with L rows and M columns. Okay, the first column of this matrix is going to be A times V1. The second column is going to be A times V2. And then all the way down to the end, we're going to have A times Vm. And then we're going to multiply it by the W vector W1, Wm. Okay, and so notice what we have here. This is a matrix times a vector. This is a matrix times a vector. So this right here, what I've written right here, this is defined. The colon means defined. This is defined to be the product of A times V, A times a matrix V. And then we're going to multiply it by W. Okay, so what this tells us, so notice we didn't even need to know the columns of A. If V is this matrix here, if V is an N by M matrix, so let me just write the definition up here. So if V, okay, so the first column of V is V1, and we're going to go up to M, Vm. If this is an N, so all of these vectors have N rows, or N entries, all of these column vectors are n-dimensional vectors, and N by M matrix and A is an L by N matrix, then the product A times V, okay, the first column of this, let me see how good this is showing up on the, okay, it's okay, but not great. The first column of this is going to be A, I'm trying to press down a little more, times V1. The second column is going to be A times V2, and then all the way up to A times Vm like this. What are the dimensions of this vector, of this matrix? Well, there are M columns, so this, we know there are M columns, so it's going to be whatever by M. Okay, how many rows are there? Well, V1 is a matrix, V1 is an n-dimensional vector, and we're multiplying it by an L by N matrix, and so the number of rows is going to be L. Okay, so this is an L by M matrix. Okay, now in general, and by the way, again, if you're looking at this and you're like, I don't remember that definition, that matrix, multiplication definition, again, I remember something like, taking the first column of the matrix and multiplying it, and that's going to give me the top entry of the first column of the product, and then I'm going to take that same one and multiply it by the second row, that's going to give me the second row of the first column of the product, and I'm going to take the second column of the matrix on the right, flip it on its side, and multiply it that way, that's going to give me the top row of the second column, and so on and so forth. If that's sort of how you remember doing matrix multiplication, yes, this is the same exact product, but just stated this way. I also think this gives an explanation for why matrix multiplication, or one of the reasons that matrix multiplication is defined the way that it is. I remember when I first learned it, like in high school or something, I was like, this is crazy. It just seems like there's an obvious way to multiply matrices. You just multiply the entries, and you've just picked something crazy to multiply, some crazy definition of matrix multiplication just for no particularly good reason. But there is a very good reason, and that's simply because we want the matrix multiplication, that definition, we want that definition of matrix multiplication to reflect the fact that it is a composition of linear transforms, and that's what it does here. At least that's one of the reasons that we want to define matrix multiplication the way that we do. Now, in general, if we have two matrices, I'm going to say W and V. Let's say this is an N by M matrix, and let's say this is an L by N matrix. Okay, for this product to be defined, these two dimensions, which are called the inner dimensions, must be equal to each other. Okay, matrix multiplication, for this to be defined, these inner dimensions must be equal to each other. And then the product is always going to be given by the outer dimension, so L by M. Okay, so whenever we have something like this, we can quickly read off whether or not the multiplication is defined N by N, and whether or not, and in what the dimensions of the output are. This is something that's helpful. So, for example, when I was preparing the lecture for today, there's product of matrices that we're going to get to, and I kind of know what the matrices should be, but I just want a sanity check, okay? Because if I have a product of two matrices, because there's also, I can often make these kind of so-called off by one errors, okay? If you've done programming before, you kind of know what an off by one error is, and I sort of class these together where I kind of have the right idea, but I've just implemented it a little bit wrong, okay? So I can sort of, one sanity check, which I'll sort of mention in the next video probably, or the video after that, is that if you have a product like this, this tells you for it to be defined, the inner dimensions need to be equal to each other, and the product is going to be given, or the dimensions of the product is going to be given by the outer dimensions. Okay, one last thing that I want to say in this video. We talked about matrix vector multiplication. We defined matrix multiplication based on a definition of matrix vector multiplication. But we can actually go the other way as well. We can sort of go back to that definition of matrix multiplication that you learned about taking one vector and putting it on its side and doing all this sort of thing. We can take that as the fundamental definition of matrix multiplication, and then we can view vectors as N by 1 matrices and define, just use that definition, matrix multiplication, to define matrix vector multiplication. Okay, this also lets us define things like, let's say, V transpose times a vector times a matrix V. It lets us define things like this as well. If V is a vector, its transpose means you just put it on its side. Okay, and we'll talk more about transposes, but again, that's something I'm assuming that you remember from linear algebra, and if not, read sections 1.1 through 1.6. It's in there somewhere toward the beginning, I think around section 1.3 or something, but that's something that you can look at for yourself. Okay, so in this video, I did a sort of, I defined something that you had already seen, which is matrix vector multiplication and matrix multiplication, but I took time to make this video because I really want to emphasize the fact that a matrix times a vector is a way to take linear combinations of the columns of the matrix, and matrix multiplication, and why that's defined the way it is, and how we can view matrix multiplication as giving us a composition of functions. In the next video, I'm going to talk a little bit about inner products. Again, that's something that I'm assuming that you know, so please read that before you watch the video, because you're not going to get everything that you need to know from the video. This should be a review. I'm going to tell you a little bit about inner products and orthogonality, and then in the video after that, I'm going to talk to you about something called the Gram-Schmidt process. If you've taken a linear algebra class, you've probably seen it, but it might be one of those things that you're like, yeah, I remember, but I don't remember. Okay, anyways, all right, that's it for this video.